This video will show you how to perform linear regression and study the correlation between two quantitative variables using Excel. So I have this data, two variables. One is oxygen consumption, the other is run time per mile, actually in minutes. And the goal in this project is to first study the correlation between the two variables and try to use runtime per mile to predict or to approximate oxygen consumption. So usually the first thing we do for this type of problem is make a scatter plot. Okay, now in Excel, if you try to make scatter plot, you have a response variable which you want to model or predict, X variable, which is the predictor or explanatory variable. You want to make scatter plot, the Y variable or data for Y variable should be on the right side, right? So what I want to do is now I'm going to do a copy and paste to move them around, okay? And delete the first column so that we're in good shape. So if you select this range of number and click recommended chart, actually it will give you the option, okay? The first chart is the best for it, okay? Or you can actually click insert and then click this icon here, and there are several options. You can select this one. That's also a scatter plot. All right, so either way will work. All right, so I'm going to click that. Okay, so you got the scatter plot. All right, that's click on the chart, move it to the right a little bit. Okay, so after I build the scatter plot, if I want to fit the trend line to understand what's the best regression line to fit the data, I can just click somewhere on this chart and right click. Right, it'll give me an option. I can say add trend line. So that's one thing, one option to do. Okay, and there's so many ways to go about it. Okay, and then you have these options on the margin of the table. There is a display equational chart. I can do that, so I know which one is what is the best linear regression line, best line to fit the data. I can also display the R-square. It helped me to understand how well this regression line explains the variability of the response variable, right? So that's great. I have a least square regression line now. I also have the R-square. Now I can also compute, this is a slope, right? Slope, and then this is the X variable, and this is Y-intercept. So that's how you form a straight line. You have to figure out the slope and also figure out Y-intercept, and that gets you the regression equation line. Now, can I find these slope and intercept myself? Yes. Excel has these functions, right? So I'm going to first label the slope. I'm going to also calculate the intercept. And I want to also calculate the correlation coefficient. Okay. So let's do that. Slope, I can use the slope functions. I hit equal and type slope. And open parentheses, it'll ask you to find the known y. That's actually the y values for the y variable. I'm going to select all the range of y value and then type comma. So that's the first argument, right, in this function. Second argument that you have to input is this, all the x values. So select them, and then hit close parentheses, you get the slope calculated. So look at this number and this number, they're the same. In fact, this cell actually contains a more accurate value. This one actually is truncated up to 4 decimal place, and this one has more accurate value. So if I really want to do prediction, I would use this one, right? Intercept, okay, use equal intercept. There's an intercept function, right? Intercept. Now, let me just choose that. And then select Y first, and type comma, and then okay, click and select X, close parenthesis. I got my intercept calculated. That's Y-intercept, right? Or you can say this is a Y-intercept, right? And you can also calculate the correlation. Equal correlate, just C-O-R-R-E-L. That's good enough. Open parenthesis. And you can choose the first array. Now, when you do correlation, which one goes first, which one goes next, that really doesn't matter. But it does matter when you're calculating slope and y-intercept. You want to know which is y, which is x. So that help you to build this model. Great. So you got the correlation coefficient as negative 0.93. That number very close to negative 1. That means there's a very strong negative correlation linear negative correlation between the oxygen consumption and runtime per mile. When you spend more time running per mile, your oxygen consumption get lower. Okay, so that's actually the Pearson's correlation coefficient. Now, if I want to do prediction, for instance, if I want to predict the understand or estimate those people whose runtime per mile is at 8 minutes, now what's the average oxygen consumption for those type of person? Now, this equation is for that purpose, right? So here, I'm going to label as predicted value. All right. What would be the predicted value? We're going to calculate the predicted value at 8. So I should use this formula like that, regression formula, using the slope. I'm not going to use this, negative 4.529. I'm going to use this as a slope, right? So I'm going to say equal to this number times, now I'm going to predict at 8, so time 8, x would be 8, right? So this x value should be 8. Then plus y-intercept, that is this one, okay? So instead of using this formula, I'm going to just do this, using the slope here and time the x and plus the y-intercept here. I will get a more accurate number. So that's 46.3335, right? So that's my predicted or estimated average oxygen consumption for those people whose runtime per mile is at 8 minutes. So you can do that at other minutes, okay? So that actually helped me to answer almost all these questions I like to answer. Make a scatter plot, add a trend line, find a regression equation, calculate Pearson's correlation, and I describe the correlation. And I want to estimate the average consumption at 8 minutes, so I just did that. Now, can we estimate average consumption for people whose runtime per mile is at 15 minutes? Now, this you have to be careful. The model is built for using a range of number from like 5 point something to 8 point something. So this model is good for prediction in this range, right? Because you use information from here, from this range of data. Now for 15, that's out of this range. You have no information for the behavior of this relation at that range. If you do that, you're extrapolating, and that's not a good idea, right? The model only good within the range of data that you use to build the model, okay? So if you want to use it to extrapolate, try to predict oxygen consumption at runtime per mile at 15 minutes, that's not a good idea. Okay, so that's it.